Point one starts out with how to write a linear equation when we're given the information, certain information, and we want to write it into slope-intercept form. So in this lesson, you will learn to write an equation of a line using its slope and y-intercept. To do this, you need to use slope-intercept form of the equation of a line. So again, just as a review, slope-intercept form, y equals mx plus b. So in example 1, they're going to ask us to write the equation. They give us the slope, and they give us the y-intercept. And so all we need to do is plug it into that equation. So we have y equals, m is negative 2, that's the coefficient to x, and then our y-intercept is at a positive 5, so it will be plus 5. Pretty simple stuff so far. Now on example 2, we're going to have an equation, or I'm sorry, a graph to give us the information for our equation. So we're going to go ahead and we're going to locate the information we need. For writing in slope-intercept form, we need to know the slope, and we need to know the y-intercept. Now, the same as when we were doing in chapter 4, we'll start out with the beginning, or the b, the y-intercept. The y-intercept is going to be, whoops, the y-intercept is not going to be that. That would be the x-intercept. Sorry about that. The y-intercept is going to be where it crosses the y-axis. So our y-intercept there is a negative 4. Now, if we need to find the slope, we can do that by using the formula for slope. So I have 2 points there. I can find the difference of the y's divided by the difference of the x's. So we'll go ahead and I'll do 0 minus a negative 4. Those are the y-coordinate points. And the x-coordinate points, I'm going to start with the same point. So I'm going to go up to 2 minus, and this time my x-coordinate point is 0. Now when you're looking at a graph, it does not matter which point you use for your y or y2 and your y1, as long as you do the same order for your x2 and your x1. So I use this point up here as my second point, and the other point right here as my first point. Just watch your integer signs and you'll come up with the same value. So 0 minus negative 4 would be 0 plus 4, and 2 minus 0 would be 2, and that is a slope that we can simplify. So it would be the same as 2 over 1. So m equals 2. Now, another way to do that, I will use the red so you can really see it here, is if I'm looking at a graph, I could just count my rise over run. So I'm going to go up 1. Sorry, doesn't like it sometimes when I do that. We're going to go up 1, 2, 3, 4, and we're going to run 1, 2. So in that way, I still would get 4 over 2, and I would be able to simplify that to 2 over 1. So our final step is we were supposed to write this as an equation. So I'm going to write it in slope-intercept form. Y equals, I'm going to apply my slope. Now in this case, it's just a coefficient, so I can leave it as just a whole number, or I could put it as 2 over 1. So y equals 2x, and this time it's a negative 4, so it's going to be minus 4. Remember, I'm not going to go back to old habits and do plus a negative. So my equation of the line would be y equals 2x minus 4. Now in example 3, we're going to get into some real life situations. So it's going to look just a little bit different. You need to be able to recognize the information, and if that is going to give us a constant term, which is our y-intercept, or if it's going to give us a rate of change, which would be our slope. So a linear model is a linear function that is used to model a real-life situation. In a linear model, the m, let's go ahead and get something we'll notice it with, The m, or the slope, is the rate of change. And remember, that is the coefficient. Let's get my e here. Coefficient to x. And then the b is the initial amount, because the b is, as we've been practicing, the b is the constant term. So let's go ahead and try doing one of these. Something easier to read though. So we're going to talk about population change in California. Now this data is a little bit older. It matches the data in your textbook. So it says write a linear equation to approximate the estimated population of California in any year between 1990 and 2005. So we're going to look at the information here underneath the photo. You can see there's a lot of population there in California. So the California population is what we're trying to figure out. So that's going to be our y in our y equals mx plus b. I'm going to go ahead and put this in here so you see the relationship. All right, now the way that they have it here is a little bit different. This is our constant term, and this with the coefficient is our change. So if we go ahead and we put in, we don't know the population, so the 1990 population was 29.76 million. Get that over here in the information under the photo. The increase per year, notice that is going to be rate. So the increase per year is going to be 0.31. And then years since 1990, and they asked us several of them, so we're going to use that as our variable. Now, writing that in slope-intercept form, I would change that slightly, and I would write it as, don't know why that came up, but getting a little disconnection with my Mimeo here. Not sure if you could see that on the recording or not. I'm going to change this into slope-intercept form. So it's going to be y equals, and I'm going to put it as, and hopefully this will write it a little bit more legibly, 0.31t plus, and I paid attention to my integer signs. Everything I had written so far was positive, so we're okay here. So my t is kind of ugly. There we go. 0.31t plus 29.76. Now if I take that and go ahead and copy that and paste it on the next page. And the magic of Mimeo, I'll go ahead and I'll move that. So it says use the equation to predict the population in California in 2005. Now they have it slightly different because they were trying to show you how to just simplify the equation. But after this, we're going ahead and we're going to graph it. I'm going to reveal the graph. And the reason I wanted to show you that was because the graph is going to show you that it could be graphed as a linear equation, which if we're graphing a linear equation, we're going to put it in slope-intercept form. So we're going to do a little reminder here. We haven't done this for a while of the unit analysis. So it says use the equation to predict the population in 2005. So in 2005, we can go ahead and put that in for our time. So we're going to go ahead and from 1990 to 2005 is going to be 15 years. So I'll change this to a black color here. So I'm going to go ahead and put that into our equation. So we're looking at population again, equals. I'm going to still leave it in the reversed form. So I'm going to have the 0.31. It's a little bit easier to see my writing there. And that was going to be my slope. That's going to show how the line is going to change, the rate of change. 0.31. And now I'm going to go ahead and I'm going to substitute in my time, which is at 15 years. And then we're going to add that to our constant term that was 29.76. And I'm going to get that this is going to equal 4.65 plus, whoops, sorry about that. I'm trying to get it so you can read this a little bit more legibly. 29.76. And so my answer is going to be that my population should be at 34,000,041. Now, if I go ahead and I reveal my graph here, you're going to see that I could check that on the graph by going to 15 years. I'm going to lock that graph so when I'm touching it, it's not going to move here. So 1 minute, please. All right, now it's locked, so I can go ahead and draw on it. So what it's telling me is when I put my time in of 15 years, so when I go here to the graph at 15 years and I follow that up on my linear equation, I'm going to see our answer of 34.41. So you can use real life situations and apply the linear equation to those. Okay, let's see if I have one more. I have one more example. Example 4 is a linear model for telephone charges. And this time it's telling me you can approximate collect telephone call charges using a linear function. This perhaps is even more dated than the California population, since we know now we use cell phones and you don't get collect calls anymore. But we'll go ahead and still perform what we need to. It says write a linear equation to approximate the cost of collect telephone calls. Use the information shown on the telephone bill to create your model. I didn't put that in there because it's a pretty large graphic, so I'm going to just go ahead and explain it to you. So first of all, you'll notice again we have our total cost. That's going to be our Y. And again, they've flipped these around, so this would actually be B plus MX. Oh, that's not legible at all. MX, because that's going to be the rate. So we don't know the total cost, but I can tell you from the phone bill on page 275 in your textbook that it says the cost for the first minute is going to be $3.44 or $3.44. That's going to matter. That's going to always be our constant. So I'm going to put that in there. Whoa, I don't know what's going on with my pen here. It's pretty hard to read some of this. So we're going to put in, try it at a different angle here and see if possibly it will. Oh, iPad fell asleep, so let me get back to it. Oh, and I've lost my connection. So I'm going to pause this real quick because the Mimeo is still going, but I have no connection. So 1 minute. And if I can get the recorder to stop.